Okay, welcome to AP Calculus, Topic 1, Unit 1, Limits and Continuity, Lessons 1 through 4. We're going to define calculus and we're going to estimate limits from tables and graphs. Okay, so I guess first of all, we just need to have a talk about what calculus is for a moment. So calculus is often explained as the math of change. And so we're often interested in how things are changing and more specifically, how things are changing at an exact instant of time. For example, let's take just a basic linear graph here. So we're able to find the rate of change on a straight line pretty easily. In fact, we've learned since algebra days that the rate of change is simply the rise over the run. So let's say this goes up 2 and over 2, and so that would be a slope of 1 or a rate of change of 1. No big deal. We could find that. Now, what's necessary, though, in order to find the rate of change is that you know 2 points on that graph. Now, on a straight line, on a linear graph, it really doesn't matter because both of those points have that same slope of 1. So if this left point represents -1, maybe this right point represents +1, something like that, then we know that the slope at -1 is 1, the slope at +1 is 1. That's not a big deal. None of that's too earth-shattering, and we don't need calculus to be able to do that. However, what if we had a graph that looks something like this? So let's go to, let's just look at a good old parabola. So maybe we will have the vertex up there at 0, 4, and some intercepts at -2 and 2, and so something like that. Well, okay. There's actually very little that we can figure out with algebra about the rate of change at any given point on this parabola. We can figure out that the rate of change right there at x equals 0 is a horizontal line, but that's just easy because it levels out and has no rise, no run right at that very instant of time. But what about finding the rate of change maybe at x equals 1? Now, we know that that point is 1 comma 3, but what is the slope at that point? And that's what calculus is going to help us figure out. That's one of the things, one of the main foundational ideas that calculus can do for us. It can do a lot more that you'll learn as you go through calculus. But calculus helps us figure out exactly at x equals 1, what is that slope? What is that rate of change at that exact instant of time? And you can imagine that at x equals 1.1, the slope is a little bit different. At x equals 1.2, the slope is a little bit different. So the slope is constantly changing because the graph is curved. So that's one thing calculus can do. Calculus will help us do all kinds of things that deal with change. Well, I suppose the first thing that we have to do is think about rate of change. And before we can learn how to find those instantaneous moments of rate of change, think about what the word instantaneous means. It means happening in an exact instant in time. That's more Unit 2 in calculus. So we're not ready for that in Unit 1. But in Unit 1, calculus starts out in AP Calculus by estimating rate of change. And really, it's just a foundational way of understanding that rate of change is built on the good old-fashioned slope formula. Now, you're more used to maybe seeing the slope formula like this, y2 minus y1 over x2 minus x1 from your algebra days. But we will be looking at many things in calculus in function form. So instead of y2, we have f of b, b being the second point, minus f of a, right? The function at b, the function at a, that's your y value, your up and down, over b minus a, that'd be our x2 minus our x1. So you do want to get used to seeing it more like this on the left side in orange. And then think of your points as a, comma, f of a, that's the y value, and b, comma, f of b. So the key thing to walk away from in this first idea is that anytime calculus asks you to estimate the rate of change, estimate being the key idea, that's not a calculus question. We cannot perform calculus. Calculus gives us instantaneous rates of change. But to estimate the rate of change, you're going to use the slope formula. Now, you might be asked to do this in a couple of ways. You might be given some type of word problem, and maybe you're told that this function s of t represents the position of a car for t time, and maybe they'll tell you that t is between 0 and 6 hours, and it asks you to give an estimate of the velocity, right? Velocity is the rate of change of the car in maybe s of t is in miles, so maybe miles per hour. Well, that's just wanting the slope formula. So you would plug 6 into s minus 0 into s, right? S of 6 minus s of 0, those are our y values, our outputs, over 6 minus 0, right? Your second x, your second input minus your first. So it's just using the slope formula. You might be asked to do this from a graph. Could look something like this. Let me zoom in here. So maybe you have a graph that starts right here. Maybe it goes up like this, and I'm not going to be too crazy here. So, and then maybe here it levels out and does something different. So some kind of piecewise graph. And maybe the question wants you to estimate the rate of change at x equals 2. Well, so here's x equals 2, trace it up, and you might be tempted to say the answer is 5. But remember that we don't want the output, we want the rate of change. Well, we can estimate a rate of change on a straight line by finding the rise over the run. Now, you don't have to find the rise over the run exactly at x equals 2, because it's part of this bigger straight line that goes from x equals 0 to x equals 3, which is a rise of 3 over 3, which would be an estimated rate of change of 1. And if there are units, you would say something per something. So that's the main idea with estimating rate of change. It's actually, even though it's not a calculus question, it is a very common question on the AP exam. Making sure that you understand the difference between estimating the rate of change versus an instantaneous rate of change, which is what we actually use calculus for. That's just not quite ready for that in Unit 1. All right, the other main idea in these first few lessons is thinking about limits. And so let's think about limits for a second. First of all, this phrase, the limit as x approaches 2, that x arrow 2, means we want to look at our graph as x is getting close to 2 of whatever our function is. So we read that saying the limit of the function f as x approaches 2. And let me just show you a quick idea here. So let's say we have some kind of nice little curvy graph here, does something fun like that. And so we can see that as x approaches 2, actually, let me draw that differently. So we can see that as x approaches, there we go, undo. As x approaches 2, so we're approaching 2, and notice I'm drawing from the left and right. This is going to be important in a second. What is the output? And we want to know the output, or the y value, or the function based on x. And of course, 1, 2, 3, it is coming to 3. So we would say the limit as x approaches 2, and maybe this function is called f, so if f of x is 3, the limit is 3. And so that's the idea of limits. Now, limits are way deeper than that, because this was easy. We didn't need any new concept or a new idea of calculus to be able to understand that as our x is approaching the number 2, whoops, thought I was highlighting there. As our x is approaching the number 2, our y is coming to 3. That's not a big deal. But where calculus really gets interesting, and this whole idea of limits really gets interesting, is whenever maybe we don't have a value that exists at 2. Because, and here's a statement that I really want you to memorize as you think about limits, and I'm going to highlight it, and I'm going to highlight it in green right here. Limits are about the journey, not the destination. Limits are not always about landing on that number 3, but what's happening as we get closer and closer to that 3 from the left side and from the right side. Now, if you are brand new to calculus, this is a very weird idea to get a hold of. Limits are not always about finding the value at that number. It's about what's happening as you approach or get closer and closer to that number. Now, what's really important is that to find a limit, here number 3, when finding limits from tables and graphs, and AP Calculus will ask you to look at tables and graphs to find limits, you must look at what happens on both the left side and the right side of the limit, so of the number you're approaching. So if you're approaching 2, you've got to say, how do we get to x equals 2 from the left side? How do we get it from the right side? And those limits must be the same for that limit to exist. So for instance, go back to this picture that I drew. So this would, not too crazy, not too weird, but from the left side, as we approach 2 here in red, okay, we're approaching x equals 1, x equals 2, getting closer and closer and closer and closer to 2, we are coming up to the number 3. And from the right side, as we come back to the number 2, we are coming down to the number 3. So the left side and the right side both are approaching the number 3. Therefore, the limit exists. However, that doesn't always happen. Let me give you an example using a table, because you will have to interpret tables of values as well. So let's suppose we have this same an xy, an input and output, and let's say we also want to find the limit as and this is called our function. So the limit as x approaches 2 of our function. All right, well, let's just suppose at 2 we don't have an answer. Maybe it's a hole. Maybe it's a vertical asymptote. Oh, okay. Probably not a vertical asymptote. I'm sorry, I should not have said that. But maybe it's a hole, right? It's a graph where there's no value at 2. Well, we have to look at how do we approach 2 from the left side and how do we approach it from the right side. For instance, maybe at 1.9, that's getting pretty close to 2, maybe we are at a value of 1.1. And then maybe at 1.99, we're at 1.01. And so what appears to be happening as we approach 2, it looks like we are coming down to the number 1, right? We're at 1.1, then we're at 1.01, and it looks like we are approaching 1 from the left side. Well, what if our right side did something different? What if maybe really close, we're at 2.01, and maybe a little farther away, 2.1. Maybe here we're at 4.9, and then at 2.01, so on the very close right side of 2, we're at 4.99. So in that case, and I didn't do a very good job drawing this because I don't have room for it, so let's kind of use some technology and scoot that down. So in that case, what happens is that from the right side, we are actually coming up to the number 5. And so you can see the left side and the right side do not match. Therefore, this limit does not exist. You can write DNE. That explains that a limit does not exist. Now, let's read another line. I'll show you another example of that. Here, this remember line right here. It says, remember that a limit is not always the same as the output value at an input. For example, there might be a removable discontinuity at the input value. Okay, so what in the heck does that mean? Well, let's look at the limit of a function as x approaches 2. So kind of sticking with the same thing here. Let's say this happens. Now, this is kind of fascinating. Maybe we curve, then we curve away. Okay, so the remember statement right here above said, remember that a limit is not always the same as the output value. See, if we want to find the limit as x approaches 2, well, here at 2, we actually get a value. It comes to 1. Whoops, let me switch to a better marker here. It comes to 1. So f of 2 gives us an answer of 1. However, that is not limit. Remember, the thing I asked you to know really well, highlighted in green here on the screen, limits are about the journey, not the destination. Now, we have seen where limits end up being the number, like here, the left and right side both came to 3. But on this case, the destination of 2, the function at 2, f of 2, gives us a number of 1, but that's not the limit. From the left side, we are coming up to the number 3. From the right side, we are coming down to the number 3. So the limit as x approaches 2 of this function is 3. So that's this. If you're new to calculus, this is a very odd idea, and it's something you're really going to have to accept and wrestle with a little bit. And the quicker you can let your brain switch to this kind of thinking, the less frustrating the next couple of lessons will be. Okay, we're almost through with the first idea. Let's look at a couple of things, and then we'll be finished. First of all, you can find one-sided limits. So sometimes the left and the right sides do not match, but we could ask only about the left or the right side. So I showed you that in a table form here, right here in the middle. The left side was going to 1, and the right side was going up to 5. Let's look at what a graph would look like of that. So let's suppose that we're going to look at the limits that goes to 2 again, because I don't know, that's just what we're doing today. And let's just say we go like that on the left side. On the right side, maybe it does something like that. Well, okay, we do have a value at 2. It's all the way up there at 3. But the limit as x approaches 2 of this function does not exist, because the left side goes up to 3 while the right side is coming to 1. And so they're two separate limits that they have to match. They have to be the same, and if they're not, then the limit doesn't exist. But I could ask a different question. I could say, and watch this carefully. What's the limit as x approaches, that's a bad arrow, 2 from the left? See, that negative sign means from the left side. Well, of the function, and that's 3, because from the left side we come up to 3. Or I could ask it differently. I could say, what's the limit as x approaches 2 from the right side? See, that plus sign means from the right side of 2. So we're always looking at the x value. X equals 2 is right there. And that comes from the right side. It approaches 1. So we can ask for separate limits, just the left side. Oh, that's a bad color. Just the left side or just the right side. And those can give us numbers. However, if I just ask for the normal limit here, circled in green highlighter, just of a number, not left side, right side, then those left and right sides have to match, or the limit does not exist. So back up here on number 4, you can find one-sided limits. That is that 2 from the right side, that plus sign means from the right side. In orange, the negative sign means from the left side. And last but not least, it is important to know that, and this is a good AP question that could appear, there are 3 reasons that limits do not exist. Now, we just saw one. Number 1 is that left and that right side, left limit, right side limit don't match. So you would say the limit D and E does not exist. There are 2 other times when limits don't exist, so let's just get this, and this will be our last thing. So here we go, 1, 2, 3. We've already seen number 1. If the left and the right sides do not match, it's D and E. Okay, maybe we're looking at the limit. All of these will be the limit as x approaches 2. The second time that a limit does not exist is if the graph oscillates at the value you're looking at. What in the world does oscillate mean? Well, right here at x equals 2, maybe our graph is doing something fine, but then at 2 it goes crazy up and down, and then it smooths back out. Well, that right there is called an oscillation. That means the limit does not exist at 2. It's going back and forth, up and down, crazy too much. And then the last time that a limit does not exist is whenever you have a vertical asymptote. And that would be a limit anytime the graph approaches infinity. So let me show you what that looks like. The graph approaches infinity. So that graph will look like this. Maybe we're still looking at the limit as x approaches 2, but from the left side, maybe it does something like that. So we never hit 2. And from the right side, maybe it does something like that. So we never hit 2. Right there in that middle, we never hit 2. And so that would also be a limit that does not exist. Okay, so there you go. There is a quick overview of calculus. The first 4 lessons, 1 through 4, defining calculus, estimating limits from tables and graphs. I hope you can say these things, or as you practice these things, you'll be able to say you can estimate the rate of change using the slope formula. You can represent limits analytically using limit notation. That just means you can say the limit of a function using our limit notation, brand new for you if you're new to calculus. Find limits using tables, find limits using graphs, and knowing the 3 reasons that limits fail to exist. All right, there's your first lesson of calculus, and I just want to say good luck.